Variography 1. There are 3 video tutorials in the variography session. The first is what the heck is a variogram? The second is calculating directional sample variograms, and the third one deals with modeling directional sample variograms. This video is in response to a request that I received from a client of mine for a short course, and the request was accompanied with a list of topics of interest. And the first topic on the list was, what the heck is a variogram? I put this video together in response to this question and hope that we'll answer it not only for my client, but for others who have asked me the same question. One of the distinguishing characteristics of Earth science data sets is their pattern of spatial continuity. And so you might ask, what is spatial continuity, and can we quantify it? Well, let's consider the following example. Here we have 2 glacial streams, and on the left we have stream profile 1. Notice the red line across the stream. That indicates the transect where sediment samples were collected at 5-meter intervals. Over on the right, we also have a red line indicating a transect where sediments were also collected at 5-meter intervals going across the glacial stream. These samples were sent to a laboratory and analyzed for the percentage of coarse-grained sand. I don't recall the exact sieve size separating coarse grain from the remainder, but that doesn't matter here anyway. There were 50 samples from each stream, and when we received these from the laboratory, one of the first things we did was look at the statistics of each set of samples. So here we see the mean for profile number 1 here. The mean percentage of coarse-grained sand is 0.8, and for profile 2 it is also 0.8. The next thing we're interested in is the variability, or the standard deviation. We look at profile 1, it's 0.269. For profile 2, it's also 0.269. Well, that's rather interesting. We didn't expect to have the same variability from both sets of samples. Furthermore, if we look at the maximum, 1.44% for profile 1 and 1.43 for profile 2, and the minimum 0.17, 0.17, they're identical, the max and mins from both streams. So the 2 sets of samples here appear identical. They suggest that the percent of coarse-grained sand from both streams is identical. And so we can ask the question, is there really any difference between the samples from each stream? If we conclude that in fact there is no difference, we would be wrong. For example, we plot a profile of each stream, and so on this 2 graphs you can see the percentage of coarse-grained sand is on the y-axis, and then here on the x-axis we have the distance in meters going along the transect from each stream. And then we've plotted the sample values of percent coarse-grained sand. And your eye tells you that this transect or profile seems to be smoother. It's not as erratic as this profile here. And so from the profile plots we see that there is a difference between the 2 stream samples. But the univariate statistics failed to detect that difference. And so obviously we need an additional statistic to describe or distinguish one profile from the other. Let's zoom in on profile 1. So here I've plotted the first 70 meters with their profile values from stream 1. And I'm going to introduce something here called a separation vector, which appears here. Notice this little white arrow indicating a separation vector. And it's placed with its tail at the distance 5 meters from the stream, and the sample value at that location is 0.74. If we go to the head of the vector, which is the vector has a length of magnitude of 5 meters, we see a sample value of 0.82. So we have 2 sample values that are referenced by that vector. What do we do when we have 2 sample values? Well, let's make a table. So we make a table over here, and we'll have two columns in this table, and we'll plot the sample values that are at the tail of the vector and the sample values that are at the head of the vector. So 0.74, 0.82. Then we'll move the vector over, as we see on the graph here, and now 0.82 is at the tail, 0.92 is at the head. We move the vector up again, 0.92 at the tail, 0.95 at the head, and do this one more time, 0.95, 1.06, 1.06, 1.09, and so on. So we can keep moving this vector across and pairing samples that are separated by 5 meters, and in this case, to the east. So we have these two columns of data then that we have generated from our one profile, and we will develop something that we call lag 1 statistics from stream profile 1. From these two columns of data, we can compute some statistics. For example, we can compute the mean of samples at the tail, which is 0.805, the mean, which is at the head, 0.8, the tail standard deviation, 0.271, the head standard deviation, 0.269. These are called lag statistics, and we will see in some of the later videos that lag statistics can be extremely helpful evaluating directional sample variograms and understanding why they appear the way they do appear. There's one more statistic that we can calculate from the lag 1 data, and that's the correlation between those values at the tail and those values at the head. Often when we have two columns of data, then we can plot them in a scatter plot, so the tail on the x-axis, the head values on the y-axis, and this plot appears like this. And you're probably familiar with the correlation coefficient, which is between the values at the tail and the head, and in this case it's 0.8940. Next, I'm going to go to lag 2 statistics. So we put in our separation vector, and here it's gone to separating samples that are at 2 lags or 2 locations, and in this case that would be 10 meters apart. So at the tail we have 0.74, and at the head of this vector 0.92, and we continue doing this, 0.82, 0.95, 0.92, 106, 0.95, 109, 0.106, 1.06, 1.11, and again we have two columns of data, one column at the tail of our separation vector, the other column at the head of the separation vector. Again, from these two columns, we can calculate lag 2 statistics. This is again from the stream profile 1. We get the tail and head means, the standard deviation from the head and tail, and we get a correlation coefficient then between these two columns of data. And we can keep doing this for lags similarly for lag 3, lag 4, lag 5, lag 6, and so on. Here I'm showing you a summary of scatter plots from 5 different lags. So this is lag 1, which we have seen, lag 2, and then we did a lag 3, lag 4, lag 5. So the pairs, the separation, the actual length of the separation distance for lag 5 would be 5 sample locations, each at 5 meters, so that would be 25 meters. And so we can see from the sequence of scatter plots that the correlation coefficient is decreasing. For example, here we have 0.89, 0.81746455. We conclude from this that as the distance between pairs of samples increases, the correlation between the samples is decreasing. And we can plot that information in another graph, which we will call the Correlogram. And so here we plot the correlation coefficient versus the lag or separation distance. At lag 0, we have a correlation of 1. That's perfect correlation of a sample with itself. and then was 0.8953. 0.8195 was a second lag 2, and so on. So this is our Correlogram. More often than not, you'll see these plotted as a line diagram. Let's do the same thing with the profile that we have from Stream 2. So here I've zoomed in on the Stream 2 profile from 0 to 80 meters and plotted the profile here. And let's generate our lag 1 statistics. Start with a separation vector of 5 meters to the east, and we pair 0.49 with 5.2. Then we move on 5.2 with 8.7, and then 8.7 with 7.7, and then 0.77 with 5.4, 0.54 with 0.6, and we keep moving across the stream profile until we reach the end, pairing samples at the head and tail of the separation vector. Then we calculate the head and tail means and the head and tail standard deviations from both columns of data. Here we've plotted the tail values on the x-axis and the head values on the y-axis, calculated the correlation coefficient minus 0.1338. And we continue doing that. And so here we have summarized the correlation coefficients and the scatter plot from 5 different lags. If we look at the correlation coefficients, we see minus 0.1338, 0.0612, minus 0.0695, minus 0.14, 0.029. These are very, very small correlation coefficients and basically suggest that there is very little, if zero, correlation between samples, no matter what their separation distance is. And so we can plot that information on a Correlogram. Again, at lag 0, we have perfect correlation of the sample with itself. But then at lag 1, we have minus 0.1, and then 0.1, and minus 0.1. We've rounded off the decimal places here. And so you can see from the Correlogram, as the way we've plotted it here, that basically at all lags the correlation is essentially bouncing around 0. It's essentially 0. So clearly then the Correlogram distinguishes profile 1 from profile 2. So the two sets of samples are not the same. When we realize that, we start looking at the Correlogram. And more generally, the Correlogram estimates the correlation between 2 points in space. And the correlation then is a function of separation distance. The correlation may also be a function of separation direction. For example, had we collected sediment samples in the direction of stream flow, they show quite a different Correlogram. The separation vector defines both the distance and direction between sample pairs. There are other popular estimators of spatial continuity besides the Correlogram. For example, we have the covariance function. The covariance function is very closely related to the Correlogram, as we will see in the next slide. We have the Semi Variogram, which we will also explore deeply in the next few slides. And then we have variations of the Semi Variogram, such as the pairwise relative, the matogram, and so on. There are others, but these are just a few. If it seems odd that we have more than one estimator for spatial continuity, think of it this way. Suppose that you live in a city block and you wish to know the distance of your block between the cross streets. Well, there are several ways that you could estimate this. One, you could pace it off. You know that your average distance of each pace, count the number of paces. That would be one estimate of the distance or the length of your city block. Another method, you might have a GPS unit. So you could go stand at each cross street in the block, record the coordinates, do a calculation, and that would be another estimate. You could get in your car and drive from the length of the block and note the difference on your odometer, and that would be another estimate of the distance. So in the same way that we have estimators of distance, we have estimators of spatial continuity. Some of them are better than others in certain situations. We will discuss more of this in the next video, where we look at calculating directional sample variograms. Let's look at the covariance function. The covariance function is simply the Correlogram. What I'm circling here is the Correlogram. This little notation, rho, is a function of the separation vector. H is your Correlogram. If we multiply that by the standard deviation of all of the samples located at the tail of the separation vector times the standard deviation of all of those samples located at the head of the separation vector, then we will have something called the covariance function. The relationship between the Semi Variogram and the Correlogram is a little bit more complicated. So here's our standard Cartesian graph, x-axis, y-axis, and then we have this 45-degree line. That's provided the scales on these two axes are equal. Any point on this line has the coordinates x equal to y. Let's give ourselves a point out here with the coordinates x, y. If we think about the moment of inertia, let's say that this point has a mass of 1, and we could calculate the moment of inertia by mass times the distance, and that's the perpendicular distance to this line. So if we know that distance, then we can calculate the moment of inertia. So you can see that as a point is out here further away from the x equals y line, it has a larger moment of inertia. It points closer, have a smaller moment of inertia. So how can we calculate this distance? Well, let's consider direction directly parallel to the x-axis up to the x equals y line. Now, because we're parallel to the y-axis, the x-coordinate hasn't changed. So the x-coordinate is still x. And because that point is on the line x equals y, then the y-coordinate is equal to x, so we can simply say xx. So this point has a coordinate xx. The distance between this point and this point, then, is simply that x-coordinate minus this y. So it's x minus y. If we look at the blue lines here and close it off with this part of the x equals y line, we should recognize that we have a 45, 45, 90-degree right triangle. So there's 90 degrees there, 45 here, 45 here. And if we remember our geometry, the ratio of the sides are 1 to 1 to root 2. And so if we take that information and think about what is this distance, the ratio of this distance to that side is the question mark to x equals y, and that's the same ratio as 1 to root 2. The question mark, or the unknown distance then, is x minus y divided by root 2. Now let's consider the lag1 scatter plot from profile 1. Here we have a great number of points, and so given that prior slide, the information, we can calculate the distance from each one of these points to this x equals y line. Now in order so that we don't have positive distances canceling negative distances, we'll just square the distance. And we'll take the average squared distance between all of these points to the line. So this equation is exactly that. If we look at what's inside of these large brackets here, we see 1 over root 2, percentage of coarse-grained at the location I, minus a percentage of coarse-grained at the location I plus H. So we recognize this formula inside the large brackets from the previous slide. And we're going to take then and summarize all of these distances, square them, summarize them, and then take the average by dividing by n, where n is the number of points here. Then we have the average squared distance from all points to the x equals y line. Let's take this formula and just kind of simplify it a little bit. We'll take this large square here and move it inside of the bracket. So that means we're going to take 1 and square it, which is 1. And the root 2 squared is 2. So we can take this 2 outside of the brackets and move it over outside of the summation sign, and it appears down here. So we have now 1 over 2n. Inside the brackets then, we move this square sign to the smaller set of brackets, and so we have the quantity inside the smaller bracket squared. I've taken and substituted the capital letter Z for percent coarse grain sand. Capital letter Z, if you read geostatistical literature, often represents any variable. So it could be gold, could be copper, could be percent coarse grain sand, and so on. So here we have that the semi-variogram is equal to 1 over 2n summation the difference between the sample values at the tail and head of the separation vector squared. So that is the official definition of the semi-variogram. Let's take that definition of the semi-variogram and apply it to the 5 lag statistics that we had in profile 1. So we're looking at the semi-variogram versus the separation vector, and remember we had correlation coefficients of 0.89, 0.81. These were decreasing, correct? In the bottom here we have the variogram. Now this is the variogram as a function of the separation vector 5. Remember lag 1 was samples that are separated by 5 meters. 0.008 is the semi-variogram value. For lag 2, that's a separation distance of 10 meters, 0.013, and so on. So 019, 027, 035. So you can see we're going from 00008 to 035. This 035 is 4 times the magnitude of lag 1. So definitely an increase in a measurement or estimator of spatial continuity, whereas the Correlogram was a decreasing function. However, both of these estimators quantifying spatial continuity. So let's look at the variogram values for profile 2. And again, in the bottom here, I have plotted the values calculated at lag 1, lag 2, and so on. So we have 0.080, 0.067, 0.078, 0.083, 0.071. A couple things to notice. Whereas the correlation coefficient could be negative, the semi-variogram value can never be negative, because remember we're squaring things, which gets rid of all negative values. The other thing to notice is that these numbers are pretty close to the same thing all along. 08, 07, if you round it off, 08, 08, 07. And again, it's bouncing around somewhere 075 or something like that. As a point of interest, if we go back to the original statistics and note, the global variance of the data is 0.073. That compares pretty closely with these numbers up here, doesn't it? So that's an interesting feature which we will explore in the next video. Let's wrap up this video then by looking at the official equations for our 3 spatial continuity estimators. I prefer to start with the covariance function. This part of the covariance function, after the minus sign here, you can find in any ordinary statistical textbook. There's nothing new there. What we have done, though, is subtract it from the global variance of our variable. And when we do this, that basically takes a covariance function, turns it upside down so that it's an increasing function and looks like the variogram. If we examine this term here and go up to the Correlogram, you will see that it's identical except for the fact that we have divided by the standard deviations of the samples at the tail and head of the separation vector, and that gives us a Correlogram, or the correlation coefficient, which we subtract from 1, and again we do this to turn it upside down so that it looks like a variogram. And finally, we have the semi-variogram, and I think that this is a pretty simple equation, but the thing to notice here is the 2, which gives it the name semi, and now you know from this video where the 2 comes from and what is a semi-variogram. That's it for Variogram 1. Thank you.